Friends, welcome to my channel. Dhanesh here.
A chatbot is a conversational agent capable of answering user queries in the form of text, speech, or via a graphical user interface. In simple words, a chatbot is a software application that can chat with a user on any topic. Chatbots can be broadly categorized into two types: task oriented chatbots and general purpose chatbots. The task oriented chatbots are designed to perform specific tasks. For instance, a task oriented chatbot can answer queries related to train reservation, pizza delivery. It can also work as a personal medical therapist or personal assistant. On the other hand, general purpose chatbots can have open ended discussion with the users. There is also a third type of chatbots called hybrid chatbots that can engage in both task oriented and open ended discussion with the users. There are two approaches for chatbot development. One is learning based chatbots and rule based chatbots. Learning based chatbots are the type of chatbots that use machine learning techniques and a data set to learn to generate a response to user queries. Learning based chatbots can be further divided into two categories: retrieve based chatbots and generative chatbots. Rule-based chatbots are pretty straightforward as compared to learning-based chatbots. There are a specific set of rules. If the user query matches any rule, the answer to the query is generated. Otherwise, the user is notified that the answer to user query doesn't exist. So we are doing the rule-based chatbot development with Python. That's what we are going to do in this implementation. I am using Cosine Similarity algorithm, NLTK, and the TF-IDF vector. Cosine similarity. See, cosine similarity is the cosine of the angle between two vectors. See, in math, there are quantities can be classified into scalars and vectors. Scalars are physical quantities having only magnitude. Vectors are physical quantities having both magnitude and direction. You are aware of these things because we learn it in math. See, when we consider vectors, see, scalars obey the ordinary rules of algebra like addition, multiplication, everything will, scalars will follow the same rules of algebra. If I am giving example for scalars, mass, time, these are all scalars. Vectors, one classic example I can give you is force. Force is an example. At that time, we have to tell the direction as well. When you consider force or electric field or magnetic field, you need to consider the direction as well. Such quantities, we call it as vectors. And one important point is vectors don't obey the rules of algebra like addition, multiplication, how scalars can be added. For example, 5 kg mass plus 5 kg mass, it is 10. 5 plus 5, 10. But vectors, it is like 5 Newton plus 5 Newton can be 10, can be 0 or some other value. So vectors won't follow the ordinary rules of algebra. For vector multiplication, there are two types of rules we follow. One is the scalar product for vector multiplication and another one is the vector product. So this is scalar product and vector product. These two are for the vector multiplication for vectors. The cosine similarity is coming from the scalar product. So I will discuss it, how it is. The cosine similarity we are defining from the scalar product of vectors. I am not discussing about the vector product here. Cosine similarity is the cosine of the angle between two vectors. It is the product of two vectors divided by the product of the two vectors magnitude. That means how we are defining scalar product, it is like a dot b, this is the formula. A vector A dot product, we will denote dot. For cross product or vector product, you will put a cross here in between A and B. So A dot B is equal to A into B into cos theta. So this is the formula we use here. A dot B is equal to AB cos theta. See, what is A? This is vector A. What is this? This is vector B. What is A here? Magnitude of vector A. What is B here? Magnitude of vector B. What is theta here? Theta is the angle between vector A and vector B. Theta is the angle between vector A and vector B. So A dot B is equal to AB cos theta. So from here you can write cos theta is equal to A dot B divided by AB. AB, that is cos theta. That is the dot product divided by AB. So that's what it is written here. The cosine similarity is the cosine of the angle between two vectors. It is the dot product of two vectors divided by the product of the two vectors magnitude. The cosine similarity algorithm was developed by the Neo4j labs team, and it is not officially supported. The closer the cosine value to 1, the smaller the angle and greater the match between vectors. That means we know the values of cos. See, cos 0 is equal to 1 and cos 90 is equal to 0. You know, in math we learn it. Cos 0 is equal to 1 and cos 90 equal to 0. That means the closer the cosine value to 1, that means the smaller the angle and the match between the two vectors. Cosine similarity is generally used as a metric for measuring distance when the magnitude of the vectors does not matter. That is very important, when the magnitude of the vectors does not matter. This happens, for example, when working with text data represented by word counts. So these things we can use it in NLP when we work with text data. Where it used, cosine similarity is generally used as a metric for measuring the distance when the magnitude of the vectors does not matter. This happens, for example, when working with text data represented by word counts. That means text data means when we are working with NLP, we use this. A commonly used approach to match similar documents is based on counting the maximum number of common words between the documents. But this approach has an inherent flaw. That is, as the size of the document increases, the number of common words tends to increase even if the document talk about different topics. The cosine similarity helps overcome this fundamental flaw in the common words or Euclidean distance approach. This is the math behind cosine similarity. I already discussed cos theta is equal to A dot B divided by modulus of A into modulus of B. This one, when we use is, see any vector, see vector A, if its coordinates, so this is a vector OA, if its coordinates is X, Y, Z, OA can be represented as xi plus yj plus zk. This is vector A. In the same way, vector B can also be represented. Then A dot B is equal to, if this is x1, y1 and z1, and vector B is equal to x2i plus y2j plus z2k, then A dot B is equal to x1 x2 plus, that is the product. So this term you will get it as A dot B is equal to, that is the formula you use, A dot B is equal to x1 x2 plus y1 y2 plus z1 z2. This is the formula for dot product. If it is in this form, in unit vectors, I, j, k are the unit vectors. I is the unit vector along x-axis, j is the unit vector along y-axis, and k is the unit vector along z-axis. So vector A is equal to x1y, x1i plus y1j plus z1k, and vector B is equal to x2i plus y2j plus z2k. Then A dot B is equal to x1 x2 plus y1 y2 plus z1 z2. This is A dot B. So that value you can substitute. What is modulus of A? See, modulus of a vector here, the mathematical formula is root of x1 square plus y1 square plus z1 square. That is the modulus of vector A. In the same way, modulus of vector B is equal to root of x2 square plus y2 square plus z2 square. So that is modulus of, in terms of x and y. So from that, if we are generalizing this, we can write it in this form: sigma of 1 to n ai bi plus sigma of 1 to n ai square plus 1 to n bi square. That is a dot b. So that is the math of cosine similarity. Mathematically, it measures the cosine of the angle between two vectors projected in a multi-dimensional space. In this context, the two vectors I am talking about are arrays containing the word counts of the two documents. Algorithm. We call it as word frequency algorithm as well. TF-IDF algorithm or word frequency algorithm. TF-IDF stands for term frequency inverse document frequency. This is a technique to quantify a word in documents. We generally compute a weight to each word which signifies the importance of the word in the document and corpus. This method is widely used. It is a widely used technique in information retrieval and text mining. And it is easy for us to understand the sentence as we know the semantics of the words and the sentence. The computer can understand any data only in the form of numerical value. So for this reason, we vectorize all of the text so that the computer can understand the text better. Now we will see these are all the terms this is the math of TF-IDF. See, TF-IDF, that is equal to, this is the equation you need to understand. TF-IDF is equal to term frequency into inverse document frequency. Term frequency is TF. I will tell you what is term frequency. We will be discussing what is inverse document frequency. IDF we are going to discuss. See, T, the letters we are using, T means term or a word, term or word. D means document or set of words. N means count of corpus, and corpus means the total document set. These are all the letters we use in the coming discussion. So the TF-IDF, the formula for TF-IDF is the term frequency into inverse document frequency, IDF. Let's get into try to understand term frequency. This is very simple. See, this measures the frequency of a word in a document. Term frequency measures the frequency of a word in a document. When we are vectorizing the documents, we check for each word's count. In worst case, if the terms doesn't exist in the document, then that particular TF value will be 0, and in other extreme case, if all the words in the document are same, then it will be 1. The final value of the normalized TF value will be in the range of 0 to 1. Now, term frequency TF is how often a word appears. See, in the simplest way, we can define term frequency TF is how often a word appears in a document divided by how many words there are. For example, the formula for term frequency is number of times term or word T appears in the document, the whole divided by total number of terms in the document. For example, you have a document with 1,000 words in that document, and you want to find out the term frequency of the word, pen. You want to find out the term frequency of the word pen. So pen is repeated how many times in the document? Let us assume that it is repeated 10 times. If it is repeated 10 times, How do you calculate? It is 10 divided by 1000. It is 10 divided by 1000 is the answer. See what is 10 here? For example, you are calculating the term frequency of the word pen. This is the word pen. The term frequency of the word pen in the document. The word pen repeats 10 times. Number of times the word pen comes in the document is 10. The total number of terms in the document is 1000. Then what is the term frequency? It is 1. This is equal to 1 by 100. This is the way you calculate it. This is term frequency. Now I will discuss document frequency. This is rarely you use, and I will explain what is document frequency as well. This measures the importance of document in whole set of corpus. This is very similar to the term frequency. The only difference is that TF is frequency counter for a term T in a document D, whereas DF, document frequency, is the count of occurrence of term T in the document set N. That means DF is the number of documents in which the word is present. So that is another term you will use in this algorithm, that is document frequency. See, another important point, this is really important, you need to understand here is the inverse document frequency. See, what is inverse document frequency? See, we already discussed term frequency is how common a word is, how common the word appears in a document, that is term frequency. Inverse document frequency, IDF, is how unique or rare a word is, that is inverse document frequency. The equation for inverse document frequency is logarithm of total number of documents, the whole divided by number of documents with term T in it. That is the formula. See, you have the log of total number of documents. See, logarithm of, it's a log to the base E. It is not underscore. It is log to the, it is, the formula is log to the base E. Here, then total number of documents divided by the number of documents with term T in it. This is the inverse document frequency. For example, if you have 10 documents, see, you have the total number of documents with you is 10. This is 10. Number of documents with term T in it will be, you can see, let us assume, more easier way. I will, then it would be more. See, let's assume that we have 1000 documents. The number of documents with term T in it is, we have only 10. So you will take logarithm of 1000 divided by 10. Logarithm of 1000 divided by 10. See, what is logarithm of 1000 by 10? That is log of 1000 by 10 is 100. Right? What is logarithm of 100? It is 2. So 2 is the, you can take it as the inverse document frequency. Inverse document frequency is how unique or rare the word is.
Start the development. First, I will import the required libraries. Let me do that. Let me run this. I have imported NLTK, NumPy, Random, all these libraries I have imported, and I'm going to use a beautiful soup for library to parse the data from Wikipedia. And furthermore, Python's regular expression library RE, will be used for some, pre-processing tasks on the text. Next step I am going to do is the creating the corpus. As we said earlier, we will use the Wikipedia article on tennis to create our corpus. The following script, the script I am going to write retrieves the Wikipedia article and extracts all the paragraphs from the article text. Finally, the text is converted into the lowercase for easier processing. Let me do the script. Let me write it. So this is the script, for the, for creating the corpus. See, let me first run this. Yeah, it's working fine. If you see this URL, this is the input to our chatbot. Input in the sense from this only it learns the, text and gives the output. So this article, this is the input to our chatbot. It takes this data from the Wikipedia and process it. Fine. Next step I am going to do is text pre-processing, and I will be writing a helper function for that. So we need to pre-process our text to remove all the special characters and empty spaces from our text. If you are familiar with the NLP life cycle, this is the step next we need to follow, that is the text pre-processing. Let me write the script for. Let me run this. Yeah, it's working. So we need to divide our text into sentence and verse since the cosine similarity of the user input will actually be compared with each sentence. So for that, we are going to execute the next script. Fine, it's working. Now we need to create a helper function that will remove the punctuations from the user input text and will also lemmatize the text. Lemmatization refers to reducing a word to its root form. You may be familiar with the stemming and lemmatization. Lemmatization is more accurate compared to stemming. For instance, lemmatization of the word ate returns eat. The word throwing will become throw, and the word words will be reduced to bird. So like that. So let's write the script for. Let me run the script. So in the script, we first instantiate the WordNet lemmatizer from NLTK library. Next, we define a function perform_lemmatization, which takes a list of words as input and lemmatize the corresponding lemmatized list of words. The punctuation underscore removal list removes the punctuation from the past text. Finally, the get underscore processed text, correct, get underscore processed text method takes a sentence as input, tokenize it, lemmatizes it, and then removes the punctuation from the sentences. Now, how our chatbot responds to greetings? See, since we are developing a rule-based chatbot, we need to handle different types of user inputs in a different manner. For instance, for greetings, we will define a dedicated function. To handle greetings, we will create two lists, greetings underscore inputs and greeting underscore outputs. When a user enters a greeting, we will try to search it in the greetings underscore inputs list. If the greeting is found, we will randomly choose a response from the greetings underscore outputs list. Let me write the script. Here you can see the script. Greetings underscore inputs and greetings underscore responses, and I have written a function generate underscore greeting underscore response as I discussed. Here the generate underscore greeting underscore response method is basically responsible for validating the greeting message and generating the corresponding response. Now, how we will respond to user queries, how the chatbot responds to user queries, as that's what I'm going to discuss. So here we are using two algorithms. One is the TF-IDF vectorizer and the Cosine Similarity. As we said earlier, the response will be generated based upon the cosine similarity of the vectorized form of the input sentence and the sentences in the corpora. Once again, this is very important. The response will be generated based upon the cosine similarity of the vectorized form of the input sentence and the sentences in the corpora. The following scripts I am going to write imports the TF-IDF vectorizer and the cosine similarity functions. Let me do that. Let me run this. See, from sklearn, I have imported the TF-IDF vectorizer and the cosine similarity. Now we have everything set up that we need to generate response to the user queries related to tennis. We will create a method that takes in user input, finds the cosine similarity of the user input, and compares it with the sentences in the corpus. Let me write that method. The generate underscore response method accepts one parameter, which is user input. Next, we define an empty string tennis robo underscore response. We then append the user input to the list of already existing sentences. After that, the following lines, right? Word underscore vectorizer. So those lines will we initialize the TF-IDF vectorizer and then convert all the sentences in the corpus along with the input sentence into their corresponding vectorized form. And the line you can see here, similar underscore vector underscore values, that is equal to cosine similarity. So that what it is doing is we use the cosine similarity function to find the cosine similarity between the last item in the all underscore word underscore vectors list, which is actually the word vector for the user input since it was appended at the end, and the word vectors for all the sentences in the corpus. Similar underscore sentence underscore number, that is we sort the list containing the cosine similarities of the vectors. The second last item in the list will actually have the highest cosine after sorting with the user input. The last item is the user input itself. Therefore, we did not select that. Finally, we flatten the retrieved cosine similarity and check if the similarity is equal to 0 or not. You may be familiar with the flattening. It will convert the spatial dimension into channel dimension. That it convert the two-dimensional matrices into one-dimensional vectors. If cosine similarity of the matched vector is 0, that means our query did not have an answer. In that case, we will simply print that we do not understand the user query. Otherwise, if the cosine similarity is not equal to 0, that means we found a sentence similar to the input in our corpus. In that case, we will just pass the index of the matched sentence to our article underscore sentences list that contains the collection of all sentences. So that's what this function is doing. I have explained you clearly. Now let me run this. Fine. It's working fine. Now, how do we chat with the chatbot? So as a final step, we need to create a function that allows us to chat with the chatbot that we just designed. To do so, we will write another helper function that will keep executing until the user types by. Code I will explain after writing the script. Let me write the script. We will first set the flag continue underscore dialog to true. After that, we print a welcome message to the user asking for any input. Next, we initialize a while loop that keeps executing until the continue underscore dialog flag is true. Inside the loop, the user input is received, which is then converted to lowercase. The user input is stored in the human underscore text variable. You can see in the code. If the user enters the word buy, the continue underscore dialog is set to false and goodbye message is printed to the user. On the other hand, if the input text is not equal to buy, it is checked if the input contains words like thanks, thank you, etc. or not. If such words are found, a reply most welcome is generated. Otherwise, if the user input is not equal to none, the generate underscore response method is called, which fetches the user response based on the cosine similarity as I explained. Once the response is generated, the user input is removed from the collection of sentences since we do not want the user input to be part of the corpus. The process continues until the user types buy. You can see why this type of chatbot is called a rule-based chatbot. There are plenty of rules to follow, and if we want to add more functionalities to the chatbot, we will have to add more rules, and it's easy here. Anyway, let me run this script. I didn't run it. Fine. Yeah. So you can see, hello, I am your friend Tennis Robo. You can ask any questions regarding tennis. I am asking who is Federer? Federer. Fine. Enter. Yeah. Roger Federer is considered by many observers to have the most complete game in modern tennis. Next question I am asking who is Nadal? Let me see what's the answer. Yeah, Tennis Robo is telling Nadal is regarded as the greatest clay court player of all time. See, when I typed bye, goodbye, and take care of yourself. So after that, there is no further dialog box appeared.
Thanks for watching. Please like, share and subscribe. Thanks a lot.